Any questions? Anyone about to come up with a question? Okay. So on Monday, we talked about momentum and the fact that momentum is conserved. All based upon Newton's second law and this idea that two objects will interact for the same amount of time with each other. So let's sort of explore those other ways we can look at the exact same thing, except this time we're going to multiply some vectors here. When we multiplied yesterday or Monday, we did a vector times a scalar, and it just distributes normally. But there's a dot in between there on purpose. This is known as a dot product. It actually has three different names: dot product, also called a scalar product, also called an inner product, but that's just there for trivia. I will sort of go back and forth between these two. Anyone want to take a wild guess why it's called a scalar product?
Because it's the product of a scalar.
It's a product of vectors. I feel like you were sort of on the right track, but
Does like the direction cancel out and it becomes a scalar?
close enough. It's because the product is a scalar. It's not a product of scalars, but is a scalar. So this is going to be equal to a scalar. So the question is, how do you get rid of the directions? What's going on there? Well, when you're doing a dot product or a scalar product, you multiply same directions. So if I have a vector, we'll start in rectangular coordinates, so let's assume I hat, j hat, and I have 3 I hat plus 4 j hat, dot product with negative 2 I hat plus 1 j hat. Let's make that not 1, but 5 j hat. You multiply the parts that are the same direction. So you would multiply 3 times negative 2, which is
-6.
plus, so you multiply those, and then you multiply these parts.
20.
And you end up with
-14.
take 2.
14.
All right. So the scalar product of those two vectors is 14. In terms of sort of polar notation, to do it properly, you would need trig, which is out of scope for the course. But if I've got a vector going in that direction, we'll call that A, and a vector going in this direction, we'll just call that B. If I did a dot product of A dot B, then what I would do is I figure how much of A is in the direction of B. So I sort of break A up into its parts. So I have this, what I'll call A parallel and A perpendicular. And I would multiply the part of A that's in the same direction as B. So this would just be that part of A that's parallel times whatever the magnitude of B is. So the part that's perpendicular has no effect on the dot product. And just a quick side note for those who have had trig, if this angle here is theta, then A dot B is the magnitude of A times the magnitude of B times the cosine of theta. If you have no idea what cosine of theta is, don't worry about it. That's just a side note for those who have seen it before. Or if you don't know about it and you're really curious about it, come and ask me later. All right. So for dot products, I am multiplying parallel parts. So if I do I dot j, what does that equal to? The I hat versus j hat, dot j hat, they're perpendicular to each other. What would the product be? Yes, 0. Because with dot products, you're multiplying parts that are parallel. There's nothing parallel here. They are perpendicular to each other, 0. If I did I dot I,
2i.
you just added it.
Oh.
R squared.
Which would be suppose I wrote it differently. Suppose I wrote it as 1 I hat plus 0 j hat dot 1 I hat plus 0 j hat. I wrote it that way. Think about what we did over there.
1.
Now, if you wrote I hat squared, whenever you're squaring a vector, it is assumed it is a dot product. There is another type of multiplication, but a vector squared would just be the magnitude of that vector squared, which is just 1 times 1. Which of that people tell me is 1? Yes,
I may
Lloyd.
have missed it, but is this the same as imaginary numbers?
No, different I.
Okay.
Yeah, we have only 100 letters if you use uppercase, lowercase, Greek, and our alphabet. We have only 100 characters, so we've run out. We have to reuse. Yeah, this is definitely not the -1i. Square root of -1i. All right. I'm going to do a little side note of the other type of multiplication. We're going to get to it in I guess, chapter 8. This is chapter 7 stuff. The other type of multiplication is called a cross product, symbolized by the X, cross product. Also called a vector product, and also called an outer product. And that last one there is just from trivia. So if I had A cross B. All right, so first off, anyone take a wild guess why it's called a vector product?
Product is a vector.
Yes. Although if you talk to math people who are really pedantic, it's a pseudo-vector or an axial vector. But as far as we're concerned, or any physics course taught here, vector is fine. So I'll just call it C. And it is not a scalar product. We're not multiplying parallel parts. What do you think we're multiplying here?
Perpendicular.
Perpendicular, absolutely. And sort of the clue is that the cross here are basically perpendicular line segments. Well, not the way I drew it, but it's basically a memory trick. So that's something that will show up later. Oh, I guess one other thing. Questions to hear before I talk about not unit vectors multiplied by themselves, but full vectors. A dot A.
One.
not 1. This was 1 because the magnitude was 1.
Oh.
Suppose I take my 3i hat plus 4j hat. If I wanted to figure out the magnitude of this, how long this vector is, what would you do?
Are they like directly perpendicular to each other?
Yeah, assume I hat is this way and j hat is that way. How would you find the magnitude?
Would you square them both and then like Pythagorean theorem?
Yeah, you do Pythagorean theorem because 1 goes over, it goes 3 to the right, it goes 4 up. My resultant, there's my resultant. And if you did Pythagorean theorem, so r squared is equal to 3 squared plus 4 squared.
That's 25, right?
Yeah, so the magnitude of this would be 5. Now, if I did 3i hat plus 4j hat dot 3i hat plus 4j hat, so I'm taking it and multiplying by itself, what would I get? Again, we got a model over there.
I hat squared plus 16 j hat squared.
And what's I hat squared?
1.
And j hat squared?
Or just 1.
Yeah, just 1. So again, we multiply the things that are parallel to each other, so we get 9 plus 16, which is 25. So if this is A, so if that's A dot A, what I get is, well, I know that the magnitude of A is 5. So this is just A squared.
Would you not factor those?
Pardon?
Would you not factor those as well? Like
When you say factor what?
the parenthesis, like, because would you also have like 24?
Oh, the FOIL? Are you thinking FOIL?
Yeah.
Okay, so let's do it I'll show you, we get the exact same answer. So if we did FOIL, so you multiply, for those who have, is algebra required to go into whatever, does anyone not have algebra 1? Looking for subtle signs, it may be some looks of fear, but I'm not sensing anyone has not had it. When I say FOIL, anyone not familiar with, because your teachers might have used something else, anyone not familiar with what is meant by FOIL? All right, so when you FOIL, you're multiplying the first terms together. So you'd have 3 times negative 2, I dot I. And then, that's the first, then you multiply the outer. So I have 3 times 5 times I dot j. And then I enter the I in FOIL. I get 4 times negative 2 j dot I plus, and then I multiply the last, 4 times 5 j dot j. All right. What's I dot I?
1.
So I get 3 times negative 2 times 1, which is negative 6. What's I dot j?
0.
So that's all goes away. J dot I
0.
and J dot j.
1.
So I still get to the same place.
Oh, because the J and I, that's what I was confused about.
Yeah, yeah. So it's there, but since the perpendicular components cancel out or go to 0, it's the same thing as you multiply the parallel parts. All right, questions to here? All right, let's now bring this back into the realm of physics. All right, so I'm going to multiply force times displacement, doing a dot product between force and displacement. Based upon Newton's second law, what is force equal?
Acceleration times mass.
Okay. It's interesting because most people do it the other way around, and the other day you were also going to do acceleration times mass. Is there?
I mean, not really, because I don't know. I just think of what I think of first.
Okay. Go ahead. I'll write it the way you said it. Dot, so it's equal to this. And then displacement, we're going to assume constant acceleration. So, what formula do we have with displacement in it?
Change in X over change in Y.
What is change in x? So what is delta x over delta t?
That's
Change in velocity over change in time?
No, that's different. Somebody else said it though.
Velocity.
Velocity. Average velocity more specifically. So if that's the case, if I've got this delta x over delta t is equal to this, then delta x is just my average velocity times time. Still doing a dot product there. The scalars aren't involved in the dot product, they're just brought out front. So this is the same as mass times time, and then acceleration dot v average. So all I've done is I'm multiplying the scalars up front and then the vectors. And the order in which dot products, the order in which you do a dot product doesn't matter. So A dot B is the same as B dot A, or A dot B is the same as B dot A. In math lingo, the commutative property holds. It does not hold for cross products though. All right, formula for acceleration. And Grace said it earlier, just at the wrong time. She was ahead of her time.
Change in velocity over change in time.
Yes. So this is mass times the change in time times change in velocity over change in time. Dot. How do you, when we were finding the average velocity, how do we do it?
Change in X over change in time.
Yeah, that's one way. The other way, if I gave you the list of every second what the velocity was.
Initial velocity minus final velocity, or the other way around?
You see the ballpark.
Was it, we added the first and the last and then divided by 2?
Yes, you're averaging the first and the last. All right, so this is dot V initial plus V final divided by 2. Now change in velocity. You were almost there, Emily, with change in velocity. What is change in velocity?
Acceleration.
In terms of initial and final.
Final minus initial.
Yes, final minus initial. So this now becomes, we'll sort of isolate that. Well, let's get rid of something here. I have delta t on top and bottom, so I'm just going to get rid of my time. So time does not play a factor into this. So I'm left with mass times final velocity minus initial velocity dot initial velocity plus final velocity. And that dividing by 2, well, dividing by any number is the same as multiplying by the reciprocal, so I got a 1/2 out front. So all we have to do is figure out what this is, and we're there. Where, you might ask? Well, when we get there, I'll let you know. All right, let's do some FOIL. So I got 1/2. Oh, you know what, we can. So I got 1/2 times the mass. All right, FOIL, we multiply the first one, so I had V final dot V initial. Multiply the outer ones, so plus V final dot V final plus. Inner minus V initial dot V initial plus the minus, now doing the last ones, V initial dot V final. All right. Seems like a mess, but it's going to clear up. We're going to start to clear it up now. As I said, the order in which you do dot products doesn't matter. So I have VF dot VI and VI dot VF. Those are the same thing. That's positive, that's negative, they're going to cancel out.